Hi, we've been talking about maximums and minimums of function, both local and absolute, and that's really helped us when we're trying to graph functions. But now we get into the real payoff where when the variables actually represent something in real life that we really do want the most of or the least of, now we have a way of doing it. And I think now you can understand that probably local maxes and mins are not going to be that important. We don't want just the best in the neighborhood, we want the best in the whole world, or the least if it's something that isn't good. But we know we get absolute maximums either at endpoints of the domain of the function or at local maxes. So we do have to still consider the local maxes and mins. They just won't necessarily be the final answer. So anyway, the good part is I don't really have to teach you anything new. We already know how to find absolute maxes and mins. The only hard part is going to be maybe translating words into math, into finding functions. So the best way we can do this is with examples, and I've picked 5 examples, and I'm hoping we'll go from a little bit easier one and they'll get a little bit harder as we go along. So the first one is, find the dimensions of the largest rectangle in area that can be inscribed in this parabola with 2 vertices on the x-axis and 2 on the parabola. So the first thing to do would probably be draw in that parabola, which I think we can sketch fairly easily. It starts at 12 and works down. And we're going to have to inscribe a rectangle. Well, I think once we pick a value right here, if we pick an x value and we go up like that, that determines what the rectangle is going to be. And we just want to find the one that's largest in area. So the question is, what are we trying to maximize? We're trying to maximize area. So we could call our function A. And what is that area going to depend on? Well, the area is equal to the length times the width of the rectangle. So what are our variables? Well, from the origin over to here, we usually call that x, and the distance from the x-axis up is called y. This point right here is called xy. So the area of the rectangle is going to be y times 2x. So we could just write our formula. And it's dependent, area is dependent on both x and y. Now here we have a little bit of a problem because we have one dependent variable a, but we have 2 independent variables. Well, we can't really work with that at this point. So somehow we have to get rid of one of those variables and make it just one independent variable. Well, the nice thing about this one, right there, we know what y is in terms of x on every point on that parabola. And this point is on the parabola. So we can make this just a function of x. We can go 2x, and in place of y, we can put 12 minus x squared. So we've got the function that we're trying to find the absolute maximum of. And do we have a domain? Well, we're measuring x away from here. So I think x has to be greater than 0 and less than what this point is here. Well, y is going to be 0 when x is the square root of 12. We don't even have to simplify that. So there's not a fixed domain. We don't have endpoints but we know that it can only go between here and here. And that this may be important and it may not turn out to be important. So now we have a problem like we've been working on. How do I take the absolute maximum of that? Somehow I'm going to have to take a derivative. And to avoid doing a product rule, the first thing you'd probably do is to multiply that through. So you get 24x minus 2x cubed. Now we can take the derivative and set it equal to 0 or undefined, just like we always do. We look for critical values. And what you can do now is say 6x squared equals 24, x squared equals 4, x equals plus or minus 2. And minus 2 is not in our domain, so that we know the only critical value is x equals 2. So if we put our domain from 0 to the square root of 12, 2 is inside that domain. And if I take a number less than 2, 24 minus like 6 times 1 squared is positive. And if I take something greater than 2, the derivative becomes negative. So that means our area increases up to that point and then decreases. So I think we can see from here that the absolute maximum happens at x equals 2. We don't have to consider endpoints. It's going to happen at where the local maximum is. So I think we've pretty much done it. We have to find the dimensions of the largest rectangle. So now we know that x is 2, so this dimension is going to be 4, and the other dimension is y, and y is equal to 12 minus 2 squared, 8. So we would know that answers the question, and we know exactly where to make the point. We don't want to make a really tall and skinny one, and we don't want to make a short, fat one. We want to make one right here where this point would be 2, 8. So there's our first example of a max-min problem with words. Okay, so here's another problem. There's a carnival going on, and there's a game where you get to pick 2 non-negative numbers that have a sum of 10. To get your score in this game, you have to square the first number you pick, subtract 4 from the second number you pick, and then multiply the two results together. That gives you your score. So they could make the game to get the highest score or the lowest score. So maybe we can figure out both of them at the same time, because the way to get maxes and mins is basically the same procedure. So let's see if we can answer 2 things at the same time. So first of all, what are my variables this time? I have x and y, the 2 numbers that I pick. Let's let x represent the first number and y represent the second number. So we have a restriction right here. The sum of the 2 numbers has to be 10. So we can write down a relationship that x plus y has to equal 10. And then, to get our score, what are we going to get for our score? That's what we're going to have to maximize. So let's call the dependent variable s for score. And it depends on both x and y. So what do? You take the first number x, and you square it, and then we multiply by what you get by taking 4 away from the second number. So that second number was y, so y minus 4 is what you'd multiply by to get your score. And what restriction do we have? Well, right now we have 2 independent variables, and we can't deal with that. So again, we're going to have to do something to get it down to 1. Well, we know that x plus y equals 10, so we could say y is 10 minus x. And then we could just deal with the independent variable x. So now we would have, instead of y, we would have 10 minus x minus 4. Or altogether, 6 minus x. And what's our domain? Well, x has to be non-negative. It can be 0. Non-negative doesn't necessarily mean positive. It just means it has to be greater than or equal to 0. And if y is also non-negative, x has to be less than or equal to 10. So this time we really do have fixed numbers as endpoints, 0 and 10. And then we do it the same way we did before. We're going to try to take the derivative of that, but once again, it might be a good idea to avoid the product rule and to distribute that through. And then I can take my derivative, and I get 12x minus 3x squared, and like always, I set it equal to 0 or undefined. I can factor out a 3x, and I see my critical values, if I set that equal to 0, because it's never undefined, are going to be at 0 and 4. And both 0 and 4 are in the domain, even though 0 is right at an endpoint. So if I put on the number line, here's 10, and here's 0. I put 4 on the number line. If I pick a value less than 4, like say 1, 12 minus 3 would be positive. If I pick a number bigger than 4, this is going to be positive and this is going to be negative, so you get negative. So you see your score starting at 0 goes up until you get to 4, and then it goes down. So I think we can see right from there that the absolute maximum is going to be when x equals 4. And the minimum is either going to be at 0 and 10. And we really don't have any way of finding out without actually plugging it back into the original score. So our values of x and y, what do we know? We know 4, which means y is going to be 6. We know that's going to be our maximum. The minimum is either going to be when x is 0, which means y would be 10, or 10 and 0. So let's see, we're almost there. All we have to do is get what the score would be. So if x is equal to 4 and y is equal to 6, what do we get? 16 times 2. We get a score of 32. That's the highest score we can get in this game. If we pick x to be 0, well, 0 times anything is going to be 0. So that's a pretty low score. But what happens when we pick x to be 10? We get 100, but y is going to be 0. So 0 minus 4 is negative 4. So that's pretty obvious going to be our lowest score. So if you were playing this game, if you were trying for the highest score, you'd pick 4 and 6, if you're trying for your lowest score, you would pick 10 and 0. So I think that would be possible to do by trial and error, but if the numbers hadn't come out to be so even in the answer, it's very unlikely that you'd find it with trial and error, but yet the math would find any combination that's right. I purposely made this problem to turn out so that it would turn out with nice numbers. Anyway, let's proceed to the third problem. This is a nice problem. We have a 3-foot radius sphere of ice cream, but we don't get to eat the whole thing. You only get to eat every bit that you can fit into an inscribed cone. So we're going to inscribe a cone inside of this sphere, and then we have to level it out right at the top of the cone, and we get to keep everything we can. Well, there's a big incentive in this problem to try to get as much ice cream as we can. So my suggestion would be to first draw the sphere of ice cream, and then inside of it put the cone. Now, the important part of a sphere is the center, so you should usually put the center in there. Now, what are we trying to do in this problem? We're trying to maximize the ice cream. So that would maximize in volume. And it's the volume of the cone. The sphere is already determined. We get to pick the cone. So what we want to do is maximize the volume of the cone. Well, what are the variables that we're dealing with? We have the radius of the cone. So we could call that R, and we have the height of the cone, which we could call H. So the variables here are then going to be R and H. And if you remember from geometry, the volume of a cone is 1/3 pi r squared h. So we run into that same problem. We have one dependent variable v and two independent variables r and h. So we have to get rid of one of them. And there isn't any obvious relationship. So we have to do a little bit of work. Well, one thing we can do in a sphere is draw in whatever radius we want. And we know the radius is 3. So you don't want to just go off to any random spot. That seems to be to that corner a really good spot. And also from here to here, between those two dots, is 3. Now maybe that's going to help us. Well, if you can see right inside here, we've got a right triangle. And we know Pythagorean theorem. So maybe that's going to be a good way to get our relationship. This side is r, the hypotenuse is 3. Maybe the tricky part is, what's the distance from the center down to here? Well, we know that this is h, and this is 3, so that little distance is going to be h minus 3. And now we can write our relationship. We can say r squared plus h minus 3 squared equals the hypotenuse squared. Now we have to decide, and it might make a difference here, which variable would we want to keep in the problem. Well, I can see that I can solve for not just r, I can solve for r squared. So if I say r squared is 9 minus this, which is h squared minus 6h plus 9, if I distribute that through, I get r squared equals 9 minus 9, the 9's go away, and you get 6h minus h squared. So we can replace all of r squared and have it just in terms of h. So what is it? Pi over 3 times h times r squared, which is 6h minus h squared. So we've got our function that we're trying to maximize. And do we have a domain for h? Well, you can't have a negative height, and you really can't have a zero height if you're going to have a cone, but you could have something a little bit bigger. So I'm going to just say h has to be bigger than 0, and you can't have it go bigger than the diameter of the cone. So it has to be less than 6. So we do have not fixed endpoints, but we do have some restriction on h, which may or may not play into the final answer. So this, for the third time in a row, we're going to try to avoid the product rule. But I usually like to keep constants out front and just multiply the rest. And what do I get? 6h squared minus h cubed. And now I can take my derivative. Keep the constant right out front, and you get 12h minus 3h squared. You want to set that equal to 0 or undefined to look for critical values. And I can factor out, besides that pi over 3, I can factor out a 3h. And I'm left with 4 minus h. And the 3's kind of cancel out. And if I want to set that equal to 0, because I know it's never undefined, I can get h to be 0, but that's not in our domain, and h to be 4. That's the only critical value that we have. So I'm going to put that on the number line, and it is between 0 and 6. And if I pick a number less than 4, you get a positive times a positive. And if I pick a number bigger than 4, this factor turns out to be negative. So the derivative goes from positive to negative. So the volume goes from increasing to decreasing. We don't care about the minimum. We want to get as much ice cream as we can. So the maximum is going to be when h equals 4. I would know exactly, I would probably make a different height. I would make it up to 4 and not to 3. I won't mess things up by drawing it, but it would be, this total distance here would be 4. Now, we haven't quite answered the question, how much ice cream do we get to eat? So we have to put this back in to the volume. So we have what? Pi over 3 times h, which is 4, times r squared. Well, r squared is going to be 6h, so 24 minus 4 squared, so that's going to be 8. That's what r squared is. So the total is 32 pi over 3 cubic feet of ice cream. I think that was a worthwhile problem, because I really like ice cream, and that's going to keep me busy for a while.